the okay, let's do some testing. Okay. All right. Let's put some notification on the server. I should probably also put this up. So in part 4 now. Let me also put this up here. Okay. Copy. Just so many steps. Okay. Okay. Make sure, I think I don't. I didn't start it from the right. Oh, I did start it from the right place. It just emits it as standard error. Okay, cool. All right, let's look at our notes. So this is kind of what we did last time here. This to-do would be good to tackle at some point, but I need stack trace support, which I don't currently have, and it's kind of a dumpster fire on Linux, so I might leave this for when I have time to research a little bit upstream with that stuff. So let's go ahead and go into what we're going to try and do today. So this is 1018. Okay. We're going to try and tackle these. And we are going to do this first. So we are actually going to attempt to do some hash tables today. Yeah. Yeah, so we're going to do some hash table stuff today. I actually have a Scratch app that I've been messing with that has a whole bunch of like configuration options. So I tried out a couple of different hashes. I tried out a couple load balancing strategies and stuff like that inside this application. And I even compared it to like std unordered map, which is sort of the quote unquote gold standard that's in Fred right now. I think I kind of settled on what I want to do and how I want to do it. What did I change here? Rid of those. Okay, so let's kind of cover the things that we want to get done. So there's a couple of hash tables around Fred, specifically with fonts. So whenever we load a font, we create a like the associative data container for that specific font, so we don't have to recreate it every time it's requested. We have a associative container for Unicode code points and their associated glyph information. And then we have a little associative container for spell checking, which is actually going to be the first thing that we're going to tackle. So let me kind of go over a small sort of like um, kind of a small like idea of the things that I've been thinking about. So traditionally in C plus or in C or C plus or any programming language, just like hash tables as a concept, um, there are two kind of like very popular implementations for these things. One is the so-called like open addressing implementation, which uses like something like linear probing. And then there is another one called separate chaining. So each of these have kind of their pros and cons, but with like open addressing, like let's say I have a hash table with like a whole bunch of slots like this, right? If I go to like insert X, right, insert Y, let's say that X hashed to this bucket, right? So then we put X there. And let's say and then that's kind of the idea, right? So with linear probing, it's like, let's go with linear probing just because it's the kind of easiest open addressing scheme to understand. If we have two inserts of these two elements, right, like back to back, we have X and then we have a Y, it doesn't actually matter what their data is. Like this is just kind of notionally what their keys are. But they somehow hash to the same value, which is not inconceivable. Hashing isn't it's not completely unique. It's like a known problem in computer science, right? So if they both hash to the same value, the question becomes, what do you end up doing? And so that's what these two particular strategies are designed to help you answer. Like they're trying to answer the question of what happens when you have two conflicting hashes, two keys that hash to the same thing. And so open addressing says, okay, if there's already a key there, or and specifically linear probing, right? So linear probing says if there's already a key that's in this slot, like if that slot's already taken up by a different value, then just move to the next slot, right? And if that slot's taken, move to the next slot. And until when you find an open slot, that's where you're going to put like your new piece of data. So if I went and said insert Z and like Z hashed to this value, so then Z would go here instead of going in the slot where Y would have been. That's kind of the idea. This is nice because it means that your hash table is completely flat. So there's no like extra chains to follow. There's no advanced like, oh, you know, I have all of this data, like, and I go to rehash, like, how am I gonna like put those chains in different buckets, all that kind of stuff. So some things become a little bit easier with linear probing. It's slightly easier to bring those data items into cache because they're all right next to each other. The things that get harder are stuff like, how do I remove an element from open addressing? And the general idea is that you don't use open addressing, linear probing specifically, for hash tables where you need to remove items from. Because, like, let's say I go to remove X, right? And then I have a lookup for Y. What would happen is that this bucket would now be empty. And so you go and look up for Y. So let me explain what happens actually in the case where you want to do a lookup for Y. So if you do a lookup for Y, you hash the bucket where X is. And then you do a comparison of the value here to the value that's in this bucket. And if those are unequal, then you move to the next bucket, because the assumption is, oh, there must be like, we must have used linear probing at some point in the past to move to the next bucket. And so when you hit this one, then you compare the value of y to the value that's inside this one. So then you make sure that that sort of ensures that you keep the that you sort of keep like remembering where y was, because you never want to lose track of the fact that you actually have a y in your hash table somewhere. And the same thing happens for x, right? Like we would hash to this bucket and we'd say like, oh, you know, y is here instead of a z. Let's move to the next bucket and try to compare like that key to whatever this bucket contains. But removal becomes a whole can of worms, because if I removed x here, then a lookup of y would believe that we actually didn't have anything slotted here at all. So we wouldn't move to the next bucket whatsoever. And we would simply return erroneously saying that y is not in the hash table when it actually is. There's a couple of strategies for addressing that. So for example, like if you have a whole bunch of buckets that are next to each other, some implementations will actually like redo a hash on this like little section of the hash table. And that would essentially redo the work of what you would initially do if you did this insert of just y and then just z. So that's one option. It's a little bit complicated, and I do have cases where I actually do need to remove elements from this thing. So this is kind of where separate chaining comes into play. And so let's say I have the same situation, right? I have the same insert of things, but let's delete this for now, right? And let's erase this stuff. So if I do an insert of x and x hashed here, so you fill the bucket with x, let's say. And so then we have y also hashes to this bucket. So now we're on the insert of y. And so what separate chaining does is it actually just creates a pointer to this bucket. So you end up having something that looks kind of like this, right? Or that looks kind of like this. So x is in that sort of like first slot for the bucket, or y, it doesn't actually matter. X or y are in this first slot in the bucket, and then this bucket has a pointer to the next bucket, or the next entry in this list for that bucket. And so that means that the insert of z, so z hashes here, we would just straight up insert z there. So we don't have this situation where we have these back-to-back buckets like this. But instead we sort of have like a linked list data structure that's here. There's also pros and cons to this. Obviously, one of the biggest cons are the fact that whenever you want to do a lookup of anything, you end up following this linked list data structure instead of looking in the immediate buckets, right? So it's a little less cache friendly in some ways, and sometimes it can be even more cache friendly depending on like how you lay out your stuff. But in general, it tends to be not very friendly to the cache, especially if you want to get removal in the mix here. Hi, Yoshi boy. How are you doing today? We're just talking about hash tables. And basically how I'm going to replace some of the data structures in my editor with some custom hash tables and not like standard library ones. So, yeah. You end up having this linked list data structure, but it makes it so you can actually remove elements, which is a very nice property to have. And it's a property that I actually need in the editor, which is why I think separate chaining is just kind of, it's the thing that I'm going to use for now until until performance tells me that I shouldn't be using it. Yeah, awesome. Well, feel free to stick around as long as you want, you know. No pressure to hang out, but I'm just going to be programming, so it's always good to have streams on in the background. I usually do that when I'm not streaming anyway, so cool. Yeah, good to have you around. This is what we're going to do. We're going to do separate chaining. Let's go ahead and get on it. And let's start with the simpler thing of jumping into our spell checker. So I think the first thing that I want to do is I want to get rid of these little vectors here. So here's basically what's going to happen. This stood set, it's going to go away and be replaced with a hash table. Oh yeah, it's a mess of types, huh? That sounds like, yeah, that's always kind of a mess whenever you have a type explosion inside of a package anywhere. Ugh. Let's see. We have this. I think there's only one set. Okay. Is there any map? There's no map. There's two vectors and a set. So I think the actual critical thing I need to do here is I need to retain this original implementation because I want to be able to compare the performance of the original implementation to the new one that we're going to create. I think that's going to be very critical in making sure that we have the right abstraction for all of this stuff. Okay. Oh, this one's kind of crazy. What are we doing here? Oh yeah, we're chopping the first character, going to the length. Okay. Yeah, these are going to get complicated to substitute, but I think we should be okay. Let's gather candidates step. Right, this is basically all going to be replaced with arena-based allocations. TypeScript is crazy with types having to do like public, single component, t extends, whatever. Oh, yeah. Yeah, that just seems like a massive, you could probably get yourself into a very fun hierarchy problem there. And I'm not sure how, so I haven't done a whole bunch of TypeScript, but I'm not sure how its like quote unquote generic system works. So for things like what you described there, I'm not sure if that like just having that type there means you have to have the closure of all types that could specialize that thing inside of your package as well. I know that's the kind of thing you would need in something like Rust, for example, just because of the way its pseudo generic system works. Okay. So we already have a scratch buffer here. What are we using you for? Populating assets. Okay. So I think what I want to do... So edits, this is the only piece of code that's going to be touched here. So I think what I want to do is I want to have like an if-def there. Dataset longest prefix. This is a really desperate attempt to try and find like the thing that just has the closest prefix. It's more lenient. Basically JavaScript. It won't accept anything that doesn't match the type. Oh, okay, that's a little bit better. So I mean, there's kind of like a runtime performance impact there, but I think it's probably so minimal that, you know, you just kind of get away with it. the runtime, I assume that the runtime checking of like the specialization is can get kind of complicated though, depending on how complicated the actual generic type is. Okay. So this is the piece of code that we're going to do. So we're essentially going to basically duplicate all of this work. So let me start with like a giant if zero block here. We're essentially going to be replacing all of these if zero. So if I build, this should build and link. It just means that spell checker won't actually do anything yet. Okay, now we're going to replace the guts of this stuff. So this is where we have our set. Let's try and do this by just replacing the strings first, and then we replace the set. So the strings we're going to replace with little arena allocations. Does this set have... So it just takes a stood string. Okay, I'm going to keep this over here so I can look at it as a reference. So let's try to do like these little bottom things first. So this we're going to keep for now. And instead of being string views, these are going to be my internal type. And then this is going to be a list. We should just do something like this. Okay, and then cool. So we have you taken care of. Don't need to, since we can actually return this by value, we just need to take into an arena here. Do I include arena? I do. Cool. Or actually, yeah. We're just going to create a LR node. Then one of these guys. Wait. So there's going to be a left and a right. So L is going to be so I have this like substring slice thing that I can offer, or that I can create here. So in this case, we're going through the word and we're slicing it just like this. So we're creating tiny little slices of the string inside this thing. And the question is, do we want word to also be owned by this? I don't think so. I don't think we have to. I think this thing could literally just point to slices. But maybe I'll be proven wrong later. We'll see. So let's slice this thing. So word, and this is going to be offset is 0 and length is equal to I for that one. And then the right side is going to be essentially the opposite. So we're going to go to I and then length. So length we can actually keep as -1. And it'll just be computed automatically. But I can keep it as length -1 just to make it explicit. The API itself actually handles all of these little weird edge cases, so it's like the whatever slice you make is going to be valid. So let's actually push this in here. Let's make sure we actually got it right. I always forget the name of this macro. Yeah. We're going to push this thing on. So node or and then let's increase our count. Should still compile. No, it does not. Word dot size. Okay, we're good there. So there's populate LR set. So populate deletes is a little strange. Is this the first thing that happens? Yeah, it is. That's unfortunate. So we might have to start developing our hash table here. Or, sorry, here. The reason we have it, well, I mean, I call it a hash table. Really, it's just set, but it's just a hash table without a value. That's all it is, because the key is the value in this particular case. And there's some decisions to be made, which is like, how big do we make the initial bucket sequence? I kind of want to, for now, I want to take rehashing out of the equation and just have like a bucket size that's good enough to fit like the vast majority of cases that this thing is going to hit. So it's going to take some measuring at the end of the day, which is why it's important that I keep the old code around so I can benchmark it later. Okay, but let's populate, or let's start actually just creating our tiny little hash table here then. So the first thing that I'm going to have is a struct edit node. Next. This is going to be for separate chaining, this next field here. And then the edit itself is going to be a string 8 edit. Since this is just the string of all the edits that are going to be contained within this thing, I think calling it edit is perfectly fine. Okay. edit set. Okay. So this is our buckets. Yeah, this is just going to be the total flat list of buckets, and each of these edit nodes are going to be like their own singularly linked list, essentially. And then we're going to have a uint64t count. Oops. Okay. And then we're going to have I'll just call it load for now, because it's not a load factor. Load factor is a thing where you compare the current quote-unquote load of your hash table to this like load factor, and it tells you whether or not you need to actually rehash. We're just going to call this load. Maybe I'll call it current load. Nah, just load is fine. Yeah, I think it's not very helpful to just call it current load, because it's like by design it's actually just the current load. So let me see if I'm missing anything, because I have a little mini. Right, there's capacity. So capacity are the number of buckets. Count are the number of active elements in the entire list. And load tells us how deep any of those individual lists go. Yeah, I think that's kind of the behavior we want. So the first thing we should do here are I want to kind of have it so that if you kind of insert a value, it'll do one of two things. It'll either, or first it tries to look up and see if we have something inside of that bucket. And if we don't, then it will create an entry for you and add your new value to that list. So I think this could actually be. Do I want it to return a bool? Actually, I don't think it matters for the purposes of this algorithm, because every time we in-place, yeah, I mean, we don't really care for solving this particular problem. So void, I'm going to call it push edit. And so we're going to have edit set. And then we're going to have the string 8 edit itself. Now there's a really cool thing you can do with hash tables where if the number of buckets is a power of 2, instead of using mod to get back an index, you can use and. And I think that's probably what we want to do. So as long as we keep that as an invariant when we create it, we should be fine. Yeah, I think we should be good there. So the first thing we want to do is we want to do a lookup for the thing. So like maybe we'll make lookup first. Right. But for this, it's actually kind of, it's not going to be doing the right thing, because we would end up, fetch node would also have to do the hash, and we want to do the hash anyway, so I think we'll probably just do the hash, do the right thing, and then have the hash result available to us. We got hashster. I actually just made this as a helper, just to kind of make it easier for strings to be hashed, because it's the most common thing in the whole system. So, and then we're going to have edit. Do I have util up here? do. Okay, good. So then we can pull out our index by getting the hash and ANDing it with the capacity. So, or capacity -1. Since it's a power of 2, you take off that 1 and then you AND it with all of the, OXFFF, whatever. And that will give you your bucket that you're supposed to insert this thing into. Let's do and with hash dot result 0. It's just an array of 1. I mean, I can eventually extend it to 128-bit hash if I wanted to. And it actually was for a short time, but it's completely unnecessary, especially when you're talking about widgets like this. Like 64-bit hashing is perfectly fine for all of this stuff. Cool. Okay, so we have an index. Now what we want to do is we want to find out if this index has a bucket. If it has a bucket, then, or if it has nothing in the bucket, then we know absolutely that we're going to insert a value there. If it does not have a bucket, then there's some work to do. So let's actually just pull out the bucket first. Yeah. And then buckets, right, index. So if, or it's, this is our simple case where we're literally just going to create an entry here. Do I want this to be... I'm kind of debating whether I want this to be a reference to this bucket so I can insert it and not have to compute this again. It's like, it's just such a meaningless little micro optimization. I'm not going to bother doing it. Okay. So the first thing we're going to do is we're going to create a new node. Actually, I'll just call this node so I can like revisit it. I can just reuse this on the stack. Push array, I'm going to push an edit node. Actually, this is already done for us. Because push array already zeroes everything, so I don't need to worry about this. Okay. I don't think I want to have... I think we copy this. I think we copy the edit into this slot. Yeah. And we can just reuse our arena. Otherwise, I think the lifetime of these edits get a little weird. Yeah, we want to have this arena own all of these things. Okay. Cool. And then we want to insert it in the bucket. Cool. And then we want to set count, and then so since this may or may not be the first time we see like a load happen, we're going to do set load is equal to std max of set load and 1, right? Because we have 1 is the depth of this particular node. And so if this is the first time we're visiting this bucket, then, or this is the first time we're adding anything to the list, our load is just gonna be 1. Okay. So we did the thing for that. Now comes the slightly more complicated case where we potentially have to chain these two things together. So we know we have a node. we need to walk that node. Oh, or actually, do we need to? We do need to walk the node because we need to find if this. We need to find if this particular node or if this particular chain already has this exact edit inside of it. And so this is the piece that becomes like, oh, okay, you know, this is the deduplication piece of the set. And actually, I kind of wrote a little bit of this code, so I could probably steal it. Right, so like this is the piece that does the chaining for us. But let me see if this actually matters. Yeah, we do an exact string match, and we figure out whether or not we need to insert. Yeah. And Elms helps us figure out what the load is. And so that's actually still useful. And then we're going to assume we want to insert this thing. Yeah, let's call this slot. I kind of do like that a little bit better. Slot, not you, slot. Okay. Slot dot edit, and then edit. And then so the reason we use the next is because we want to discover if we basically want to reuse the next slot to do like our hash table insert for when we get to the end of the chain. Okay, so here we're assuming there's either no next, which implies that we haven't done this work yet to figure out if the match for this slot is the match for the edit. So we're going to do that now. So let me close all my parentheses. It's Vim? No, this is actually my editor. All this code is actually for my editor called Fred. It's all natively written in C++, and it's kind of described here. So if you go there, you can kind of learn a little bit about it. There's Discord and all that stuff, so you know, no pressure to join or anything, but that essentially describes what I'm working on. Here's the website in case anybody's curious. But yeah, it's a native editor built completely from scratch in C++. No like crazy libraries or anything besides a tiny bit of STL here and there, which I'm actually working to get rid of actively in this particular section of code. Yeah, Abner is absolutely correct. Join my cause. Welcome by, Abner. Okay, right, we're back to hashing stuff. So if it's an exact match, we're not going to insert. Oops. And otherwise, we are going to insert. Yeah, pure C. I mean, I would be very close by the time I'm done with all of this arena work. Yeah, by the time I'm done with all this arena work, moving it to C would be exceptionally trivial, like to the point where it could actually be done by an LLM. Because I would say, hey, you know, go replace all the namespaces with like namespaced names, and that'll be good enough to satisfy the linker. But you know, I kind of do eventually want to get somewhere close to that because the build times are already pretty quick. It's about 3 seconds, but that's still like, to me that's still 2 seconds too long. And getting rid of a lot of the STL will help with that, but I don't know. Like back of the napkin, I've compiled a couple of smaller apps with the infrastructure I created, and it takes about 1 second. So if I can get down somewhere close to that, that would be pretty sweet. Oh, thanks for the shout out. So we'll see how fast I can get the compile times down. It's really just a matter of getting all the STL, getting rid of all the STL nonsense, template instantiations, and the gratuitous amount of templates that are there in general. I'll get there. Okay, so we know definitively we want to insert now. So I'm actually going to steal this code from up here, put it here, indent this code. New entry, right? So slot, next, new entry. So here we know we have a slot with no next, but as an invariant of this. And now we've decided, hey, we actually need to insert it. So we've gone through all the checks to make sure that we don't need to insert it. Okay. All right. That count. Why do I have this? Oh, elms, right. So because we only count elms when this next pointer is valid, the number of elms need to be bumped up here by 2. Yeah. Node. And then I will take this as well. So the load plus elms, right? That's our max. Okay, is that everything for edits, for push edit? I think that should be everything. And that should be actually the vast majority of everything we need functionality wise for this table, because we never really do another lookup besides the case where we insert, since it's sort of acting like a set. So push edit set, push edit. Push edit set. And that reads weird, but it's like more precise, so I kind of like that. Push edit set edit. So like we're pushing an edit into this edit set, essentially, is the idea. Okay, so now we can start rewriting this thing. It's string buff. Why does this need to be taken by mutable pointer? What is this thing doing here? So we have the LR set that we ended up creating from the previous thing. This is just kind of like concatenating the two. But we subster at 1? Why? What are we doing? I guess I should read my comment. Okay. Oh, right, because we're like assuming that we're deleting some character inside of this thing each time through each pass of this. Oh, okay, I get it now. This definitely makes sense. But I could do this all with my string chopping and then append those two strings together. Okay, so let me this. So in actually LR in set. Do I need this to be? It could be constref. Why not? It kind of doesn't matter. This is like the reason why you use constref over just taking it by values, because MSVC's calling convention is kind of garbage sometimes, but honestly, it doesn't make that big of a difference here. Let's see, do I foresee sections of the code base that will do its own thing without the arena parameter? Like internally using a stretchy buffer that's secretly malloc and freeze. It's just a random example. Or is everything that always requires dynamic allocation will always go through an arena allocation? My idea is that everything goes through an arena allocation. But sometimes you actually can't prevent that, right? Like if you're using a library, for example, like FreeType, I use FreeType to rasterize all my glyphs, and I don't really have control, or at least I don't have very fine grained control over how the allocations that FreeType is doing internally work. So in those particular cases, I just have to like, surrender the system to whatever FreeType wants to do. But I think in general, I want to do everything as much as I humanly can through arenas. And actually, I went through the like painstaking process of making the buffer itself arena friendly. So if I go to breadbuff here, this whole thing, it is now completely STL free. So the entire text buffer does not use the STL whatsoever. So you can even search for like stood something in here and you won't find it. And so it's all driven off of arenas that are like stretched out or compressed depending on how the insertion or deletion buffers work out. All these nodes are allocated on their own arenas, so I can play with them and like reuse their memory very aggressively. I think that in general, there's always some kind of strategy you can apply to arenas to make them act, slightly more malloc and free-ish, but still have like the really awesome lifetime guarantees that arenas give you. Right, so I won't patch it in the library. Yeah, no. I think that's just like, yeah, exactly. It's just such a huge amount of effort, and you don't know, like the only way you can possibly guarantee that your libraries aren't doing anything from underneath you is to basically like Linux gives you this thing called LD preload, which lets you essentially like ad hoc replace whatever function you want with your own library implementation. That's like the way you can get rid of like malloc and free permanently. Windows has something similar ish with detouring. Or you can try and leverage like the weak symbol linkage of like new and delete and sort of like replace those in C++. But I don't know, in general it's a really difficult problem. I think surrendering to the libraries is probably the easiest thing until you can get around to implementing those libraries yourself. Yeah. And even then, it's like the OS is going to do whatever the OS does, right? So if you're relying on like an OS API to do something for you, it still might malloc and free, and you just have no control over that. The best control you have is a handle that's just like opaquely something that the OS allocated for you, which I can live with those tiny things. But any allocation in my system that's flowing through it is either it needs to be one of those opaque like OS or library things, or it needed to have come from a arena. That's kind of the variant I want to establish. Or it's on the stack somewhere. Like sometimes I just like put a pointer on the stack like very high up, and then I can sort of reason about what the lifetime of that pointer is based on how I use it. Okay, let's close like half a dozen of these things. Cool. Cool. Yeah, and actually last week, or yeah, I guess earlier this week, I came up with this. I came up with this little dialogue that kind of shows the current arena allocations that I have, like all of the arenas across the entire system. And this is just a really good tool that I've been using to find like runaway allocations or like allocations that don't make any sense. But if you click on like any of these entries inside here, you could see like where that allocation was happening, like right here, right? Here's the push arena. But this is in our command buffer, so I kind of expect that to be huge. Anyway, that's been a super useful tool. I could even just keep it up here in case anybody's curious about how the allocations are flowing through the system. Okay. And I'm still tweaking things very much. So if R is empty. Okay, so L. Actually, let me have these. Yeah. Right, because this is just a node. So if R is empty, maybe I can do this a little earlier. So if R, we're going to continue. Actually, I don't even need braces here. If there's like a control statement that is the only child of an if statement, that's like one of the very few times that I won't use braces around if statements. Otherwise, I kind of like having braces around them unconditionally. And so the reason we needed this buff is so we can split it up and sort of like concatenate a string together. So if we want to do that here, what I want to do instead is I want to create a string list and just build them up together. Well, actually, I don't even need a string list, but I will need a Scratch arena. So begin. So since we have a potential conflict here, we're going to add a conflict here. This is just it's an array that's of size 1. It references this arena here. So Scratch. So here we get the substring of R. So we start with L. So, and then we get a substring of R. So sub R. And we chop off the first character of it. So we want to start with R, and we want to start with offset 1. And then we actually don't need length there. It can compute the length for us. Straight cat. This is why we needed our Scratch arena. And then we do L, and then sub R. And then finally, we're going to push this into our set. We don't want buff anymore. This parameter can go away. or actually, I'll call this edit. Let's compile. What did I do wrong? Insert 240. Oh, of course I forgot that. Cool. So that does compile, which means that we roughly did the same thing that we're doing here. So I think, let's just double check this. So if R is empty, which size 0, we're done. We start with R, or we start with L, and then we substring R. Right. Okay. This was just super messy C++ code even for me. I don't know what I was doing there. I think I was just like writing the algorithm as it was, like, because I essentially looked at the article that was the reference here and as a whole bunch of pseudocode. So I was like, I think I could do this. That's the idea I went with. Okay, so we got populate deletes. How about transposes? How difficult is this going to be? So we have our edits again. Let's actually just go ahead and do this right off the bat. Okay, we're not gonna, I assume we're gonna get rid of this buff, like right off the bat too. This is a very similar problem. We take the first character of the right-hand side, and then the second. And then we get a substring of those two guys. Okay, so we start with a buff that has L again. Oh, here's the other thing we could do here as like an optimization. We don't want to grow this arena like hundreds and hundreds of times potentially, so we can have something like auto inner temp, again temp, or temp, and I know I did this wrong. This is just so you can better like take advantage of the little arenas there. Temp, it's not declared. What? Oh, that would help. Okay, that's fine. It's so you can better optimize like your arena usage in this particular area, because we only need this string to live for the duration of this call, and then we're done. Okay, let's go back to transposes. I think we're actually going to end up taking a lot of this implementation here, so let's kind of copy this out. Oops, assuming I do the right thing. Then we want to take this. Just because the pattern here is like pretty similar. If the length is less than or 1. So if the size is less than or equal to 1, we're going to continue. Okay, and then we push back these two characters, and we get the substring of R. Okay. Why? What is this doing? Like, so we take the first two characters anyway, and then we substring R to its length. Oh, it's just transposing the first and second characters. Oh my goodness, that's just silly. Okay, I sort of get that. Okay. So I think what I can do instead is I can turn this into like another string cat like this. And just take our, we can just take, we actually don't need a substring at all. Because all we're going to do is we're going to take all of R, which is what this is doing, and combined with these two. We're going to take all of R and then just swap these two middle characters, essentially, is what's going to happen. So I think we can just do this. And then of R, right? Which in this new edit is exactly at L size, right? So R1 0 L size plus 1. Because L size is where R starts. And because we've guaranteed that R has at least two characters, this is valid and this is valid. So even if this is 0, which it totally could be, but no matter what this is, these two, this is valid. Okay, so we've transposed those characters and then we push the edit. That should give us what we want. Okay, now we want to populate replaces. Let's just copy this all. And this thing can be actually I call it literal. I couldn't remember if I shortened it to lit or literal, but it's lit. So we have our alphabet, and we're gonna go through and try to add alphabet. Like this U represents the union, so we're unioning all of these entries here. So we have a buffer, starts at L. So we can replace it. Right, which is L dot size. Like, this is just such messy code. I don't know why I wrote it like this initially. I think I just wrote it to get it working, and then it worked, and then I never revisited the code. Okay. This is, once again, very similar to the code we wrote up here. So let's take this and put it in here just as a template. This time we're checking for size equals 0 because we don't want it to be empty. Okay, so we remove a character of R and we replace it with one of the alphabet characters. That's the idea. So here, this does need to be a substring. Substring, and then R of 1. So this is just chopping the first character of R, whatever it is. So it could even end up as an empty string here, and that's totally fine. So substring R. But actually, I think we don't want to do this because we want to be able to replace that character. So we actually, I mean, if we copy the whole string, that should be fine. Because whatever character was in that first slot, we're going to end up replacing with whatever this thing is anyway. So I think actually if we do this, we're in a much better spot because then that kind of simplifies the allocation. Because I was trying to think of like how I'm going to get the extra character inside there, but it turns out I don't actually have that problem because this is significantly simpler if I just end up creating the edit here. So edit at L size. So because we know that size can't be 0, this is always valid. Right? And here we're going to basically loop through and replace those characters. Okay. Okay. So this is the expression we're going to use, but we're not going to use it yet. For each index in the alphabet, I inside. Yeah, so we're going to replace each one of these at that location. Is equal to this thing. Now we push this into our edit set. And that should get us the same semantic as this stuff was doing. Let's double check. Right, get R, replacing the first character of R, which is what this was doing, and that this made space for. Yep, that should work if we compile. $361. Oh. Right, I gotta get rid of this and then bring back our arena. Cool. That should do it. Cool. Let's get rid of this stuff. It's funny how much weirdly it kind of looks a little bit more complicated, but it's actually like much simpler code running underneath because I've hoisted up all of the stuff that like pushback was doing and append was doing, and I made it much simpler as a result of like this stuff. So like all it is a cat plus this thing, whereas before to make space for this thing I was doing like a whole pushback and like God knows how much code that was calling. Okay. Let's do our inserts. Okay, so this is replacements. Now we're doing actual inserts. So I will end up creating a space, like a gap between these two words. So it is almost literally this thing, with the added caveat of now we actually are making space for those things. 0, you can use this as a reference. I said this in the last stream, but a good tip from somebody who writes compilers for a living is that if you, well, C and C++ compilers in particular, is that if you want to turn off a block of code, like instead of commenting it out, like, you know, like you would normally do something like, oops, like this, right, to comment out that huge block of code. Instead of doing that, just do if 0 blocks. It's much faster, and then you can like turn it on anytime you want. In most editors, including Fred, it retains syntax highlighting, which is like useful to look after. Anyway, it's a much better method of disabling code than commenting it out, and much faster, in my opinion. So, since we need to make a gap this time, I don't think I have, or at least I don't believe I have a helper to do like a cat in place. So I have a copy, a cat, a format. But nothing to do it in place, which is obnoxious. Because I almost want this. This is so dang close to what I want, except I need an extra character inside of R to make this work. And so I think what I'm going to be forced to do is I'm going to be forced to allocate a string and then blit R and L and R into the right spots. Which is really what the cat is doing, but it's going to have to be like explicit in here, I think. Let me see how annoying it will be to write a... So cat, can I just do like a cat in place? That would be super nice. Or I could do it as a string list. Just join them. But that seems like so heavy-handed for this one thing. Let's see what the other ones are doing here. And none of these are doing anything particularly complicated. So I think that like having this one-off thing is kind of gonna be the option for me right now. Yeah, I think I'm just gonna copy it over. Or I have a single string. Okay. If I have a single string and I say that it's like, let's just do the dumb thing for now, and then I can do the more advanced thing later. So space. Actually, this does need to be. Um, yeah, I'll just do the dumb thing for now. Okay, and then since L and R, since this changes on each loop, this should be fine. Like we actually need it exactly here. So we do L and then space. So that's the concatenation of the first half. And then we concatenate R. And that's just so annoying to get one character in there. It's like, that is one reason why like pushback was kind of nice to have here, but you know what, this is gonna bug me too much. We're gonna allocate, and we're gonna allocate a string of size L size plus R size plus 1. We don't need this to even be a C-stir. Doesn't matter. C-stir just adds like an extra null byte at the end. But since this is all like internal stuff, then we don't need it. So now we're gonna blip first half. Something like this. We actually don't need to do this because we're going to override it anyway. So this is going to be stir plus 1. That's our destination. And now this is going to be R. Okay. And this should always be the place that we need it to be, where we're doing the actual insertion. So we're retaining all of R, retaining all of L. Annoyingly confusing and a little bit verbose for this, but that's fine. Do this. Oh, buffer is gone. Cool. That should do what we want it to do. Yeah, we're appending to our arena, or we're appending to our edit set again. Okay, cool. I feel much better about that, even though it's a little bit verbose. We're only doing the correct amount of work there. So we got populate inserts. That's the one we just finished. Okay, now we got to do this one. Populate edits 1. We don't need buffer. I'm going to come down here. It should actually simplify quite a bit here. Delete all of these at once. Populate LR set. Oh, we got to give it a scratch arena. Okay. Yeah. And we're going to conflict. We could potentially conflict with this. Otherwise, all of these, since they are with the edit arena, need to get that arena parameter. Yeah, otherwise this is all passed by reference, which is fine. That should still compile. Does not take 3 arguments. Oh. Because this thing is now returned. Which I like a lot better, actually. Cool. And then populate edits to 2 distances away. Okay. This one does need a scratch arena. Sure, edits has all of the edits from 1. Yeah, so this kind of like composes the previous set of edits that we had. So we have this arena here. Now the question becomes, how do we initialize this thing? Because now this is the first time when we're actually initializing one of these new edit data structures that we have. So I think what we want to do is always struggle with these names. So something like that. So since we want this to be a power of 2, I'm not sure how big we want to make this yet. So let's start with like 256 for now. 256 buckets. Which is still a power of 2. But we can better express it if we do like 1, like... No, I mean, it's having it be in code is fine. Having it be in code just like that is fine. and everything else will be initialized as 0. So set push array, and we do want it to be 0'd, so we want to do arena. There we go. Populate edits 1. So since the arena is like this, we kind of need to do a little bit of this thing to make sure that we get it. Okay, so essentially we're going to go through the edits that we just made, iterate that entire set, and make sure that we populate this edit data structure with all the edits that were in there. Now, is there a reason why we need 2 of these to do that? Why do we need 2? Oh, right, because we're recursively applying the edit to the edits that we just computed. Okay, so this is the distanced to piece of it. Okay. Okay, I get it now. I get it. This loop needs to change fundamentally though, because we can no longer get away with this for each loop. We need to do something a little bit more complicated. So we need to go down the capacity in this case. We're going to continue. Otherwise, we want to get into the bucket list here. So we want to insert into our new list, and then we want to basically take it out. So, and I'm going to call this node in bucket.first. Or actually, no, we're just going to call it bucket. And then we're going to call it and then we're going to insert. So this is going to go into the primary arena, and it's going to go into edits. And our word is going to be slot edit. And now we just do populate edits 1. There we go. Let me make sure that's going to do what we wanted to do. Yep, that does exactly what I expected to do, which is good. Okay. So here we do the comment. We can delete all this code. Okay. And then we have filter candidates. And this is what's going to remove all of the edits from the thing that we care about. And I think this is kind of like unnecessary. And the reason I believe that is that I think we actually just want a separate list to be produced from here instead of reusing the same set. This is where I was saying I don't think we actually need removal in this case earlier in the stream. Oh, sorry, first time chatter. So instead, we're gonna compose up this list that just adds all of the things that we care about. So struct edit node. Node next. Edit list. Oops. Okay. So we have spell checker and we have edit set. And the arena with which we're going to add this thing. Okay. And this loop was already kind of weird to begin with, since you're like removing elements while you're iterating the list, so it just made it kind of confusing and annoying. Having this separate list thing that we're composing is much better solution, I think. Makes it so we don't have this weird, you know, make sure that you're retaining the invariance of your data structure problem. So we're going to actually need a similar loop to this thing here. Except it's not E1, it's edit. And we're not doing this. If not, so actually, if it is valid, we want to add it to the list. Let's make a result list first. Let's make a node. This case, we're going to have candidate node. And this thing is going to hold the edit. It's equal to slot edit. What am I missing here? Oh yeah, we're going to insert. Or we're going to push it into our result list. increase our count. Okay, I don't think we need any of this code anymore. Cool. That's pretty easy. The comment's still somewhat relevant, so I'll keep it. Still a dictionary, and we're still removing the invalid elements because of this. We're going to end up with a candidate list. Let's stick the candidates on the same arena that we're having for the edits. Okay, I think that looks good. Populate edits 2. We need an arena, edits, and word. Okay, and this is the edits edit set. And you need the arena. Since all these strings are owned by this set, by the edit set, we're not going to bother allocating the or reallocating the strings for these candidates. We'll just kind of like reuse the same memory in this case, since that's kind of like what this is establishing. Like this arena is the same arena where edits live, is the same arena where the candidate list lives. I think that's reasonable. It should compile. Okay, now we got the conversion problem, which I was expecting at some point we would hit. Right, so valid. Oops. Why is this? Why do I not have Vim mode? That was weird. I think I must have fat fingered something. Eventually I want to get rid of this like valid string view, but I'll need to adjust a couple APIs to do that. But for right now, it's going to be string 8 and both of these essentially. Okay, so valid. We're just going to copy this. Initialize the data. Then we're going to try to find the word. Since this is the primary implementation we're going to call, I'm going to change this one to just dispatch to the one that has the string 8. That should work. Okay. Then we have populate dictionary. Yeah, eventually this is going to change into, or the data set itself is going to change to be arena allocated, but for right now it's not. I think that's acceptable. Okay, now we need to populate these things. So let's go ahead and open up a little scope here so we can open up a arena that's going to contain all of these things. Scratch. We don't have any conflicts this time. Okay, now we're going to gather our candidates. So Do I have a bunch of these or something? Why is this coming up so many times? I guess it was used at some point. Okay. And we give it the edits, or actually, wait a second. Gather candidates. Do you even need to take this edit set as a parameter anymore? I think it's because it's only an intermediate computation, so we can get rid of this completely. So, make edit set. I think that's all we need. Right. Yeah, because we don't need to return the set itself as a result. Just the thing that was computed off of the set. So this could be local now. That's nice. Iterate the list and add them. Suggestions. All right. Since this is still a vector, which we desperately need to change at some point. Why are you dying? Pushback. Oh, implicit conversion. That's why. Oh, what? I have never been in love with the idea that this constructor for string view is explicit. I mean, I sort of get it in some cases, but like most of the time you're just trying to get your code to compile. So it's just such a pain in the butt. Yeah, see, now it works. Because this constructor is explicit, the one that takes a string view. If the other way around, it's totally implicit. You can have a string decay into a string view, which I totally agree with. That's perfectly fine. I guess they just want to avoid the they want to make the allocation explicit in this particular case. Yeah, not the biggest fan, but you know, it is what it is. Okay, let's actually test it. Okay, so so if I hit this, okay, spell check did work. And we come up with stuff. Okay. Yeah, we come up with suggestions. So if I spell incorrectly, dwell. What? Why? I feel like something's wrong. Let's turn on the old algorithm. So this is why it was important to keep the old algorithm around. So let's create some macros up here. 0. Let's do it like this. So if old spell, right? Else all this stuff, including gather candidates, I like to do this kind of thing, right? So the STL does this. And I really violently agree with their decision because that actually just makes it so easier to view like which one's enabled and which one's like not enabled, right? So in here, I'll just copy this. Okay, turn on spelling, that works. Spell. That one came up right. Okay, so something is definitely funky about the new algorithm. The question is, how do we compare them? And what exactly is going wrong? We have both of these paths active simultaneously. That is the question. What if I just turn off this code here? Right, we get ODR violations because stuff, right? Like we've redefined some of these things, edits that type redefinition LR. This thing. Or LR, new LR. I shouldn't need it anywhere else down there, I think. Oop, we're breaking still. LR set. Alphabet. Of course, I break my convention. Okay, cool. So now I can have both of these paths active at once, which is actually pretty cool. So okay, we're gonna find out how they're different. So start with an assertion here. Okay, that should be the easiest thing to fire. So let's see what happens when we try to actually build it. All right, didn't build it. Okay, and we're actually going to fire up Rad Debugger for this. So I don't need you. Let's go to my targets. My red. Okay. And okay, let's retry. We hit a trap. Okay, perfect. It's fine. Let's go to our call stack. Okay, here we are. What do our suggestions look like here? Oh, is this one just 0? Really? Really? We didn't have a single candidate? What? Oh, that's crazy. Okay, so clearly I need to set a breakpoint up in here. Um, Red. Okay, so let's check out what's going on. Don't need you. So edit should have a huge capacity. Cool. The load is also huge. That is just like a massively massive load. The count is also huge. I mean, we have 119,000 entries in this list. So clearly I need to be adjusting. I need to be adjusting the capacity quite a bit. Yeah, we probably need to start with like at least a K for words that are fairly large. Because it all depends on how big the word itself is. Because you're going to get like basically n squared number of entries in your set. And it's all going to depend on where n is like the number of characters. Okay. That's just crazy. Okay. Yeah, we have none. Okay, well, let's try to figure out where our algorithm is going wrong. I don't want to get quite to the level of diffing these each of these like individual little algorithms. I mean, we might have to, but I hope not. Let's just kind of like check. Let's just like spot check. So populate, delete. What are we doing here? So we delete that first character. Yep. It's pretty straightforward. Skip those first two characters. Drew these guys. Makes sense. That looks right. It's correct. Because we're just getting whatever the alphabet is here and putting it in there. Yep. This is the only one I kind of suspect is doing something dumb. So we take L first, we create the gap, and then we take R after that, right? Take L first, create a gap, which is what this +1 does, and then we blit R into this slot. Adding 1 for the gap. Wait a second. No, this is right. This is right. Let me actually quickly run this with let me very quickly run this with ASAN enabled. Spell checking. Right, we hit our assertion, which is what I expect. I'm gonna abort. Okay. That looks correct. Populate deletes, transposes, replaces, inserts. Yes. What is going on here? Just making sure all my arenas are fine, because it's possible maybe I overlapped an arena somewhere. No, it should be fine. Also, ASAN probably would have caught that. So what's going on? I'm gonna try something. I'm gonna see if somehow these two things are getting, or like maybe what edit point it's getting out of sync at. So is it at edits 2 or is it at edits 1 somewhere? So in order to do this, I basically want a checker, and I want to have expected and checker together. No, because then I basically have like an ordering problem. Okay, yeah. Yeah, so we can have a checker, and if we hit, so we're gonna populate it, and then for all the edits down here, after this edits one, we're gonna pop off this thing, and for whichever edits are left, those are invalid, or like basically those were not properly computed in edits one. That's what we're gonna do. Okay. So, right. Um, yeah. So we have that. And now for checker, we're gonna erase this thing. Let's do it before we kill the arena. Or we're gonna assert this actually. Assert it's equal to 0. Why? Oh. Gosh, what's the API to do it? What is the dang API to remove it? Hey, Piggy Bank. How are you? I'm just doing a little bit of hash table stuff today. We're kind of in the middle of validating our spell checker, and there's a very subtle bug somewhere, and I'm not exactly sure yet. So we have both the new implementation and the old implementation. So the old one is not using arenas. The new one uses arenas and has my own hash table implementation. So I'm trying to figure out like where the subtle bug is. Oh, nice. Yeah, I guess yeah, watching a stream is a good pastime. Yeah, thanks for coming out. We need to find erase. Yes. What? Erase should work with this. It should work with this string view. Why is it not? Do I actually have to allocate a string here? No. There's no way. There's no way I'd have to do that. There's just no way. Hold on. Quad edit. For spell checking, are you identifying words in an identifier or something, or is it non-code spell checking? It is both. We do both. So basically, you see how like individual things are underlined. So for separators inside of identifiers, the algorithm will kind of like it'll identify pieces of an identifier that are word-like, and then mark them as, oh, you need to try and spell check this, or oh, you don't have to. And then it just checks them against the tray, which is built as a dictionary of stuff in of like a giant dictionary that I have baked into Fred. And then this piece of it, the actual suggestions piece of it, is like a complicated algorithm that's all based on kind of like a pseudo Levin or like a pseudo distance algorithm. Yeah, so I try to do the useful thing, and sometimes you want it like maybe you do want it checking everything as like one word, but I think in practice, like you just want to check the individual things between like underscores and stuff like that. Okay, so now we're trying to find out why stdset is acting this way. Why are you doing this? Oh, of course, Fred. Right. I have to construct an actual freaking string for this. I might as well do this. Whatever, we're just doing debugging code at this point, so it doesn't really matter that much. It just kills me inside. Before scratch and oh, assert, right. Do people use it often for a code spell check? I feel like I would get annoyed because of acronyms, not real English words. So there is so for things like that where you have like the algorithm tries to be a little bit smarter about that. So if you try to do like TCP/IP or something like that, it won't spell check words that are all capitalized. But if you do like ACP versus ACP here, it'll spell check the undercased one, but it won't spell check this one. However, if you do ACP like that, it will want to spell check it. But if there's any like it tries to do something like the result of that is because like Pascal case stuff like this, like you want to check this thing versus like this thing independently. So for things that are acronyms, if it's all like uppercase, it won't do it. But honestly, like it's easy enough for me to just ignore these things, for example, that I haven't found a huge problem with it. Yeah, there's a lot of when I did the implementation for this initially in Fred, I did a whole bunch of research on like what people do for spell checking and like what's like the most useful pieces of words to spell check. And I ended up coming down to like this set of semi-useful things. But you can see it's not always like perfect. But it gets me close enough and it stops me from making stupid mistakes at PR time, stuff like that. Okay. We're going to build it again. And we're going to make sure that if we hit our assertion, things go bad. Okay. Let's fire up rad debugger again. I don't need that breakpoint anymore. Okay. Okay, so we already hit our checker size, which is exactly what we want. This is great, because this means that something earlier in our algorithm is incorrect. So let's see what's going on here. So checker size. Oh, gosh. So I can't really see the size. Okay, 301. Whereas the edits 301 versus 526. I actually kind of want to see it here. So I want to restart this. Are there many configuration options? So right now there are 3 major configuration options in the yeah, you could do the list view. I should try to use that with the stood set and just see how far I can get. I might try to play with that while I'm debugging this. But in terms of configurations with Fred, right? So like there's basically these main ones. There's ASAN, there's profiled, and then there's the arena tracker mode, which lets you do this. It's like you can view all the arenas that are happening. Because they're all like non-zero cost things, I separate them out into their own configurations. But you can add them and you can compose them with each other. So like this set is like kind of combinatoric, if that makes sense. So you can combine ASAN with profiling. You can combine ASAN with arena tracking, that kind of stuff. Lots and lots and lots of useful configuration options. But I try to keep it relatively simple on top of all that. Okay. So we currently are attached with Brad Debugger. Let's figure out what's going on here. So if I try to check this, let's see what these edits look like. So 522 edits here. And E1, after we populate its edits, we have 526. So there's already a discrepancy. Like we've already computed a different number here. 522 versus 526. Okay, so we have more edits in here somehow. Are we dealing with the same words? Sublicense, yeah. Sublicense, okay. Yeah, let's try the list rule. Let's see if we can make that work with this thing. With this like checker guy. So my val, my head, left parent. Oh, this is going to be complicated. I think you need something more than just a list rule for this, because it's a tree. Yeah, well, I just actually pulled the dev branch. I kind of like pulling the dev branch because I get to play with all the stuff that Ryan's like currently working on. So I just kind of like live with the breakage and test out things early. In this case, I think the list rule does not help me. It is in the release branch though, so list is there. Yeah, list doesn't help me because this is the red black tree. Oh no, what am I doing here? No, I don't want that. I want this. I don't unpin this, sorry. Yeah, because it's a red black tree, so I need like a more advanced kind of listing thing. Yeah. Yeah, I just use dev branch. I really should. I really want to get like NatViz working with this stuff. Like, it shouldn't be too hard. You just got to get like an XML deserializer and then like parse their insane expression format. It becomes like a kind of a nightmare. But it'd be so nice to just have like all the STL visualizers just work for whatever release. Yeah, yeah, trees don't seem to be super well supported in Radebugger right now, which is like I can live with that. As long as I can keep my like flat hash tables for the most part. Right. So let me actually do a watch on here. Wait, did I kill my watch window? I must have killed my watch window. So E1. So how many of these are going to be actually broken? We could view all of our hash tables. And so each of these, yeah. Yeah, I thought it was coming at some point as well. He said that some form of it was eventually going to be there, but that it wasn't going to be like everything. Like it wasn't going to include all the features of NatViz, which I could even just live with that, but apparently there's like nothing right now. Which is annoying because like that would be such a huge way to get people to use the debugger, because NatViz is such a huge piece of technology that people have kind of like adapted over the years, especially for how much the VS debugger is used. Yeah, NatViz is definitely Turing complete because you can do all kinds, like you can traverse very complex data structures in NatViz, and you need control flow to do that kind of stuff. One example is like we have this like huge NatViz that tempted to try my own visualizers. Yeah, yeah, I should try to use his like visual like his rad debugger API to define my own visualizers. That would be kind of cool because he does have an API that you can plug in for that kind of stuff. I just haven't messed around with it yet. I just don't like I mean, I'd rather have something I don't actually have to compile in for debugging stuff. I really want it to be something separate from my code, like that lives next to my code but not in my code. And I guess the reason for that is because like debugger technology can change over time, and visualizing data can change over time, and I want to be able to like very rapidly change those things independently of the code. Exactly. Yeah, yeah, a plugin system would be great. But, you know, here we are. There's also kind of some empty entries in here, weirdly enough. I also don't know if, like, in a list, like list, it's like I want to be able to apply the list rule to all of these elements, like, recursively. And, like, maybe I can. Like, if I do list, like this, will that work? No, that just does not work, right? That simply does not work. Because this is like buckets, and each of these buckets are a list. Okay, yeah, have a good one. Thanks for stopping by. Okay. Why is this so different? Is it actually returning something useful here? Yeah, maybe I should have it assert when it like when it's when it finds an edit that it doesn't know. That would actually make a little bit more sense, I think. So if I do auto IT, and then this whole mess. Uh, let's do this. Maybe rows, lists, list. Let me try that. Yeah, yeah, let me try that. That seems like it could be the magic sauce. Um, Okay, so yeah, let's try this. So if I do rows, so we want this to be, no. What are your parameters? Let's get rid of this thing first. Okay, we have that. I wish he told you what goes in here. Yeah, I don't know. I might be too dumb to interact with this right now, but this will at least give me an idea of what's going on here. Okay, we've already crazily aborted, so let's see what happens. Sublicense. Okay, so we're already broken. And we break super early, which means that it's happening much earlier than we expect. Let's remove the checker from here. And let's start checking individual things. So if I have like, we need to get this thing in order. I need to get, how am I gonna get this identifier back? Because I actually had to hash define it to keep it like boxed away over there. Yeah, that becomes a little annoying, doesn't it? It doesn't get double replacement. That should work, I believe. Okay. This compile. No. Oh, right. I need to change this back to a string view. Here's my argument list. What's the time? It would tell you what the argument list is. Oh, here we go. Ah, it still got replaced. Of course it did. I forgot. Rack macro placement works that way. Goodness gracious. Maybe I can do like this. Nope, still doesn't defeat it, huh? New LR. Ugh. I think I might have to just delete these things for now. So if I do this, let's do this. And then what? Oh. Okay. So we have roughly a set that we can sort of work with. Okay. Okay, so we kind of want to just like iterate it like this. Fortunately, iteration is kind of a little bit more verbose than I would love it to be, but it's fine. And then we have edits. Edits. Um, okay, so assert assert that it's not equal to end. Oh, come on, what am I doing? Oh, it needs to be a dang string. This is why they invented a transparent key lookup. Or a heterogeneous key lookup. Populate deletes. Oh. right, because this is a pointer now. The annoying thing is, like, I gotta kind of measure it before it goes into recursive mode, because once it's in recursive mode, it'll assert all over the place. So I kind of have to step to the debugger on this one. Let's do. Here we go. Let's do this. 10. Okay. Cool. Populate deletes. So edits, you have a count of 10. Old edits, you have a count of 10. Okay. That should. Oh my gosh, this is going to take forever. By the time we get down here. Okay, so we know it got past there, so that if the deletes are good. The deletes I feel pretty solid about. Those are looking good. So let's kind of take all this code. And put it in here. We could binary search for this, but I think it's probably just as effective to kind of do it this way. Okay. And since we do deletes already, we also need to do transposes. Buffer. Okay. This should get us close to what we want. So deletes are good. I feel good about those. Build this. Okay. We're gonna go down here. Aha, okay, we found one already. So transposes is broken. Supposedly, at least. See, edit, the string is empty. The string is empty? Why do we have empty string? Let's look back at what our transposes are doing. So we concatenate L and R. But we end up with empty string, huh? How? Is our insertion incorrect? What? Oh my goodness, I never actually set the dang string. Oh my gosh. That's actually incredible. I'm actually amazed it worked at all. Okay. Yep. Yep. Okay, let's remove all this debugging code here. I think that's a pretty definitive bug that is probably the source of everything that's wrong. Yeah. Okay. So they probably won't be in the same, but we could have a stood set to ensure that. Hmm. We're just gonna double check here again. Um, empty. Oops. Cool. Cool. Okay. Um, Bell. Yep. I feel like that's a pretty good representation there. Cool. Um, yeah. So let's do now. So now we can finally go back to this. Our ult spell should be 0. Where is it? Okay, here we go. What? Pushback? Oh my gosh, explicit. We actually did this earlier. It's a little bit slower. At least it feels slower. But maybe that should come down to tweaking the algorithm. So let's get a stopwatch. Or let's start doing some timings now. And let's include feed. Because I want to be able to test this stuff. Yeah. I want to be able to test this stuff independently. Okay. This is the part where we can actually do both of them and just emit the times for both of them. Yeah, the suggestions actually just don't matter. We'll have them overlap. It's fine. We're just wanting to do some basic testing here. So to the feed, I have a global feed, which allows us to just push messages arbitrarily to like this thing down here. So I added support for that. That's thread safe, but because this happens on the UI thread and it doesn't happen on a background thread yet, I can just push it immediately. I just gotta remember global feed. That's what the one. Let me pull this scratch up here, or so scratch, or we want to push this data to the feed. So basically we want to have format we want to have something like percent. I think it's just an unsigned integer ms, and then this is just going to be two ms. Okay, and then feed. Should compile. Timers. Oh. Cool. So we can do, let's include the Scratch Arena setup as well. And then we can embed it here. This should give us a better picture of how our algorithm is performing now that we switch to our own hash table implementation and inform what decisions we can make to make it better. all that fun stuff. So let's see. Oh, no feed information, huh? Where's our feed? Oh, is that because... Oh my gosh, I forgot to do this. That would do it. Okay, so let's try this again. Okay, that's much better. Yeah, this new algorithm is a lot slower, right? The last one ran 170. This is like over 10 times slower. So let's try and tweak some things here. Obviously, the first thing to tweak is how big the hash table is. So for example, like if we do kilobyte 1, make a 1K table. One kilobyte worth of pointers. Is that going to be better? Let's see. Okay, so it's a little better. It's not, still not quite performing. See, it outperformed the old spell check there, which is nice, but it definitely did not outperform it with a larger word. So that's interesting to me. I'm not sure why it's so poor with the larger words. And I doubt making the hash table bigger than what it is now is going to be huge. Like, this is probably going to have, like, depreciating return, but let's see. No, it actually made it better. I mean, that actually made it quite a bit faster. Now let's see how it compares to like a release build. Build release. Because this has the capability of really flying on the, like, the stid set can be optimized pretty aggressively. So let's see. Let's make sure we're actually release. Yeah, release. Okay. F10. Okay. Yeah, so this is kind of what I was meaning, where like the stid set version can be pretty aggressively optimized. Although the new one is much better still, even for short words. Or for short words, it's still better. Why is it being invoked multiple times? That's a little weird. I'm not sure why it's invoked 3 times. That's kind of strange. Suggest. Yeah, I'm not sure why that's invoked 3 times. Oh, because it's like literally however long I'm holding down the mouse. Okay, that's fine. Yeah, the long words are really rough. Um, does a bigger hash table make sense there? Like, does it still keep helping? Let's just scale it out super far and see what happens. Like, let's double it again. Nope, I need to build release. It did. It actually did make a difference. Oh man, I'd be really interested what the arena sizes look like in this situation. Yeah, that made like a huge difference actually. So it does kind of scale pretty well with size. Um, let's see how much this is impacting the arena size though. So let's pull up our arena tracker. And let's watch peak size in particular. Right. I mean, it's not that big. I mean, you do get some pretty fat strings in there. And honestly, that particular table isn't even showing up really well here. Like I would have expected spell check. Yeah, it's not even like registering. I mean, I feel like that's probably pretty okay. However, I imagine if I created like a huge table, like what if I created like an 8 MB table, for example? Okay, so if we pull that up and we sort by peak size again, do arena. Okay, so spell check, we expected that to happen. Okay, so now if we do this, whoa, we exploded. Why did we explode? Tracker snapshot. So We died down here somewhere. Why did we die there? That's very strange. So let's kill it, I guess. And then we'll launch it from the debugger. Oh, 10. Okay, so here we are. Is that because the arena is erased by the time we pull the snapshot? So there probably needs to be a write back first. Okay, well, I mean that's definitely a problem for another day. I will certainly have to fix that soon. Okay, but so we know that messing around with this, you play with based on input size. I think we really need to drive it based on the input. I think that's going to be the only reasonable solution here. Anyway, we've made really good progress here. We basically got this over to arenas, and it's working pretty well. And I think we can get similar, if not better, performance out of our hash table versus what the versus what we're getting out of the std set implementation. It's all just a matter of making sure that we can take advantage of those slots, take advantage of the individual table slots, yeah, and all that good stuff. Okay, anyway, I think I probably got to end the stream here. It's been a little bit of a crazy day, but we got a lot done. It's very good. Anyway, thank you everybody for tuning in, and I will see you next time.